A altruistic friend, like well-known critics to whom I am thankful for letting me know my negatives. At the outside, I wish you and your beloved a safe journey in 2021 too. In spite of the 2 waves of corona, with the third wave very much imminent real soon, all with high mortality rates, besides other natural calamities all over the globe. Social activist come good-hearted teacher Professor S. Suresh back with altruistic delight. This video on angle of publication on YouTube today, 18th August 2021, Wednesday. The topic for today is semiconductor shortage, causes and consequences. A semiconductor material has an electrical conductivity value by falling between that of a conductor such as metallic copper and an insulator such as glass. Conductivity falls as its temperature rises. Metals behave in the opposite way. Its conducting properties may be altered in useful ways by introducing impurities or doping into the crystal structure. When two differently doped regions exist in the same crystal, a semiconductor junction is created. The behavior of charge carriers, which includes electrons, ions, and electron holes at these junctions, the basis of diodes, transistors, and most modern electronics. Some examples of semiconductors are silicon, germanium, gallium arsenide, and elements near the so-called metalloid staircase on the periodic table. After silicon, gallium arsenide is the second most common semiconductor, and it is used in laser diodes, solar microwave frequency integrated circuits, and others. Silicon is a critical element for fabricating most electronic circuits. Semiconductor devices can display a range of useful properties such as passing current more easily in one direction, showing variable resistance and sensitivity to light or heat. Because the electrical properties of a semiconductor material can be modified by doping and electrical fields or light, devices made from semiconductor can be used for amplification, switching, and energy conversion. The conductivity of silicon is increased by adding a small amount of 1/8 of pentavalent or trivalent atoms. This process is known as doping, and the resulting semiconductors are known as doped or extrinsic semiconductors. Apart from doping, the conductivity of a semiconductor can be improved by increasing its temperature. This is contrary to the behavior for metal, in which conductivity decreases with an increase in temperature. The modern understanding of the properties of a semiconductor relies on quantum physics to explain the movement of charge carriers in a crystal lattice. Doping greatly increases the number of charge carriers with a crystal. When a doped semiconductor contains free holes, it is called p-type, and it contains free electrons, it is known as n-type. The semiconductor materials used in electronic devices are doped under precise conditions to control the concentration and regions of p dopants. A single semiconductor device crystal can have many p and n-type regions. The p-n junctions between these regions are responsible for the useful electronic behavior. Using a hard point probe, one can determine quickly whether a semiconductor sample is p or n-type. Some of the properties of semiconductor materials were observed through the mid-19th and first decades of the 20th century. The first practical application of semiconductors in electronics was the 1904 development of a catch detector, a primary semiconductor diode used in early radio receivers. Developments in quantum physics led in turn to the transistor in 1947, the integrated circuit in 1958, and the metal oxide semiconductor field effect transistor MOSFET in 1959. A large number of elements and compounds have semiconducting properties, including certain pure elements, are found in group 14 of the periodic table. The most commercially important of these elements are silicon and germanium. Silicon and germanium are used because they have 4 valence electrons in the outermost shell, which gives them the ability to gain or lose electrons equally at the same time. Binary compounds, particularly between elements in groups 13 and 15, such as gallium arsenide, groups 12 and 16, groups 14 and 16, and between different groups 14 elements. Example: silicon carbide. Certain compounds, oxides, and alloys. Organic semiconductors made of organic compounds, semiconducting metal organic frameworks. The most common semiconducting materials are crystalline solids, but amorphous and liquid semiconductors are also found. These include hydrogenated amorphous silicon and mixes of arsenic, selenium, and tellurium in a variety of proportions. These better known semiconductors have properties of intermediate conductivity and rapid variation of conductivity with the temperatures, as well as occasional negative resistance. Such disordered materials lack the rigid crystalline structure of conventional semiconductors such as silicon. They are generally used in thin film structures which do not have higher electronic quality, being relatively insensitive to impurities and radiation damage. Almost all of today's electronic technology involves the use of semiconductors, with the most important aspect being the integrated circuit (IC), which is found in laptops, scanners, cell phones, etc. Semiconductors for ICs are mass produced. To create an ideal semiconducting material, chemical purity is paramount. Small imperfection can have a drastic effect on how the semiconducting material behaves due to the scale at which the materials are used. A high degree of crystalline perfection is also required, since faults in the crystal structure interfere with the semiconducting properties of the material. Crystalline faults are a major cause of defective semiconductor device. The larger the crystal, the more difficult it is to achieve the necessary perfection. Current mass production process uses crystal ingots between 100 and 300 mm in diameter, grown cylinders and sliced into wafers. There is a combination of processes that are used to prepare semiconducting materials for ICs. One process is called thermal oxidation, which forms silicon dioxide on the surface of the silicon. This is used as a gate insulator and oxide. Other processes are called photomasks and photolithography. This process is what creates the patterns on the circuitry in the integrated circuit. Ultraviolet light is used along with the photoresist layer to create a chemical chain that generates the patterns for the circuit. Etching is the next process that is required. The part of the silicon that was not covered by the photoresist layer from the previous step can now be etched. The main process typically used today is called plasma etching. Plasma etching usually involves an etched gas pumped in at a low pressure chamber to create plasma. A common etched gas is chlorofluorocarbon, or more commonly known freon. A high radio frequency voltage between the is what creates a plasma in the chamber. The silicon wafer is located on the cathode, which causes it to be hit by the positively charged ions that are released from the plasma. The end result is silicon that is etched anisotropically. The last process is called diffusion. This is a process that gives the semiconducting material its semiconducting properties. It is also known as doping. The process introduces an impure atom to the system, which creates a p-n junction. To get the impure atom silicon wafer, the wafer is first put in 1100 degrees Celsius. The atoms are injected in and eventually diffused with the silicon. After the process is completed and the silicon has reached the room temperature, the doping process is done and the semiconducting material is ready to be used in an integrated circuit. Chip shortage typically there is some sociological or physical change that prevents certain chips from being produced in large enough numbers to satisfy demand. A severe case of chip shortage occurred in 1988 after a pact between American and Japanese chip manufacturers resulted in severely reduced production. Changing to newer production methods also causes chip shortages as the new factories are not built quick for the newer chips. An example of a shortage of smart card chips in 1999. Another was during the rationing of other types of chips in 2004. The 2011 Japanese earthquake led to a period when it was difficult to source all the parts needed for various systems. Chip shortages can have a major effect on the electronics industry, where manufacturers change the sourcing of chips and suffer major loss of profit, such as when PC manufacturer Gateway switched from Intel to AMD microprocessors in 2000. Some manufacturers may find themselves having to redesign their products to take account of the shortage of certain chips, or have to leave design options open to allow alternate chips to be incorporated into the design. In 1988, there was a shortage due to the high demand. Workers at 7 Hitachi Corporation factories had summer vacations to meet the demand. In 1994, there was a shortage due to new technologies being developed. The newer manufacturing process required significantly cleaner clean rooms, and many batches of integrated circuits are discarded due to manufacturing errors. Intel suffered a shortage in several products of several products in the year 2000, large companies were able to receive the products they needed, but this gateway had to wait to find other chips. There was a lack of CDMA chips in 2004. This was due to the strong push of mobile phone companies to introduce and establish CDMA in both the US and India. After the 2011 earthquake in Japan, there was a severe chip shortage of NAND memory and displays. Qualcomm releases on April 19, 2012, that they expect a shortage of the Snapdragon chip due to the lack of facilities to manufacture the 28 nanometer chip. The COVID-19 pandemic caused disruptions in supply chains and logistics, which coupled with a 13% increase in global demand for PCs, owing to some countries shifting a stay-at-home economy, key chips necessary for the manufacturing of a broad swath of electronics. The pandemic's impact on the manufacture of semiconductors in South Korea and Taiwan was cited as a cause for the shortage, with a constrained supply impacting industries as broad as console gaming and the automobile industry. In February 2021, market analyst IHS Market were cited by the BBC as forecasting the impact of the dearth to last enough to the third quarter of 2021. Lead times on chip supply at this time had already extended 15 weeks, the longest lead time since 2017. By April 2020, for semiconductors from Broadcom Incorporated had extended to 22.2 weeks, up from 12.2 weeks in February 2020. At the end of first quarter of 2021, used car prices in some countries were increasing due to the demand for both economic recovery as well as a chip shortage. Some automotive manufacturers increased the selling price by as much as 10% in first quarter. The 1986 US-Japan Semiconductor Trade Pact was designed to help US chip manufacturers compete with Japanese companies. This resulted in severe cuts in Japanese production. The 1993 DRAM chip famine was caused by a factory explosion at which produced 60% of the world's supply of resin used in chips. From 1993 to 1994, there was a glut of chips, and companies lost incentive to build new leading-edge factories. When the new generations came out, there were not enough factories to produce the new chips. An earlier chip famine might cause a slump in the market, which would result in fewer chips being manufactured. Slump is over, the demand might grow too high for the companies to fulfill, resulting in a second shortage. New generation chips are difficult to produce due to manufacturing capabilities. Batches of product are discarded due to manufacturing defects in the first few runs, resulting in manufacturing capacity that could have gone to producing older chips not being used to ship newer chips either. Furthermore, customers often want the newest chips available and may not be willing to settle for older chips. So companies must wait for newer chips to put into the products. Conversely, older chips can also be subject to chip shortages. Other chips made on old equipment can easily go into shortage if demand spikes because the production lines have already been fully depreciated and optimized. There is no easy way for chip foundries to scale up the production to older chips because the capital costs of setting up or expanding chip production lines are so high that they are economically justifiable only for new lines featuring the latest technology. This is what caused global shortage of older chips in 2021 during the COVID-19 pandemic. The CHIPS Act, enacted in 1986, was designed to help the US compete with Japanese manufacturers. However, it had unintended consequences. The act called for Japanese companies to stop selling chips below dumping, which led to the companies producing and exporting fewer chips, the root cause of the dumping. American companies did not re-enter the market as expected due to the high cost of production and risk. The 1988 chip famine caused the delay of Zelda 2. The adventure of Link due to lack of stamps, shortages of DRAM, SRAM, and process have led to rises in the prices of the remaining chips. Lack of ICs for the Y console was a global Y shortage in 2007. The 2021 global chip shortage is an ongoing crisis in which the demand for is greater than the supply, impacting more than 169 industries and has led to major shortages and queues amongst consumers for video cards, video game consoles, cars, and other electrical devices. Cause of the global chip crisis is a combination of different events, with the COVID-19 pandemic being the primary reason. Other causes have been attributed to the China-US trade war and Taiwan. Due to the COVID-19 pandemic, more people had to stay home and upgraded the electrical devices such as webcams, monitors, and computers in order to stay in touch and be in the fourth quarter of 2020. Traditional computer sales saw a 26.1% growth over the previous year. In 2020, the US government placed restrictions on Semiconductor Manufacturing International Corporation, biggest chip manufacturer, which made it harder for them to sell to companies with American ties. These restrictions forced companies to use their manufacturing plants like Taiwan Semiconductor Manufacturing Company Limited and Samsung. However, these companies were already producing at maximum capacity. In 2021, Taiwan experienced its worst drought in more than half a century, leading to problems among that use large amounts of ultra-pure water to clean the factories and wafers. Chip weight. Okay, for example, TSMC's facilities use more than 63,000 tons of water a day, more than 10% of the supply of two local reservoirs. Top 10 companies manufacturing semiconductors are Intel, Samsung Electronics, Taiwan Semiconductor Manufacturing Company, SK Hynix Incorporated, Broadcom Corporation, Qualcomm, Micron Technology, Applied Materials, NVIDIA Corporation, and Texas Instruments. Here are few sobering facts. All semiconductor chips began as a silicon wafer that takes approximately 90 days to process into a chip. American semiconductor manufacturing companies account for 47% of global chip sales, but 1% of the global manufacturing is accomplished in the US. Demand for semiconductor chips has increased nearly 50%. In September 2021, Chinese telecommunications giant UI Technologies Company Limited was banned by the White House from buying computer chips made with American technology. Unfortunately, UI had already stockpiled chips before the ban became effective, and its rivals did the same. China Semiconductor Manufacturing International, known as SMIC, similarly received US government restrictions in December 2020. The result, SMIC has found it challenging to sell its finished products to companies with US ties, keeping it working below full capacity. With the production capacity tight and demand rising, chip manufacturers were challenged to absorb both shocks, fear of having Chinese chip factories placed on an entity list. Fixing not only the shortage issue but the risk issue will take not only a lot of time but a lot of money. Problem is systemic and has been dictated by financial math that has incentivized what we currently have in the behavior of anyone who runs a chip company and can add. We need to put in place financial incentives, local decrees, legislative incentives, and use a multiple of layers to change the current dynamics of the industry. Even with all the written motivation in place, it will take years for the physical implementation of the incentivized changes. TSMC has been under enormous pressure for years about a fab in the US. Now they are planning one in Arizona that is still years away. Will be old technology when it comes online and will barely be a rounding error. All that from a multi-billion dollar effort, but it's a start. A real effort is likely to be well north of 100 billion US dollars and 10 to 20 years in the making before we could get back to where the US was in semiconductor industry 20 years ago. As the saying goes, buying semiconductor equipment company stocks is like buying a basket of the semiconductor industry. It can also be viewed as the arms merchant in an escalating war. It does not matter who wins or loses in the chip industry, but building more chip factories is obviously good for the equipment makers. In general, in the near term, foreign makers such as Tokyo Electron international NOVA measuring and others may make for an interesting play. There is plenty of time as we are sure that no matter what happens, we will see zero impact from government sponsored activities in 2021, and it will likely take a very long time to trickle down, so we could beware of knee-jerk reactions that may drive the stocks near term. So it is quite clear that there are no quick fix solutions for semiconductor chip shortage problem. Supply needs to increase to keep pace with the increasing demand and compatibility attributed to the proliferation. Till then, companies may have to redesign the products and reduce the demand for semiconductors if feasible. I know it is not easy. Anyhow, we need to tide over the situation. We are experts in this field. We need to analyze the situation and then come up with the requisite action plans. Pragmatic. Debates, discussion on topics like this. Topics like this can go on forever. Anyway, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements, views expressed solely mind based on limited knowledge gained over 6 decades of personal experience. Always watch these videos with closed caption, subtitles for absolute 100% comprehension as per my sincere recommendation zillion times so far. I know I rushed through to complete the presentation within 20 minutes maximum. This time limit is self-imposed to read. I am quite aware of the fact that I exceed this time limit. Sometimes I take double or triple this time depending on the topics, since I make honest attempts to cover the selected topic more elaborately, including so many intricate findings. In particular, Wikipedia quite extensively, besides articles and books published recently. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay possible to maintain social distancing attributed to pandemic novel COVID-19 and prolong your lifespan, lead a healthy life. God, also known as the Supreme Power, is the one and only one who can put a stop to natural, unnatural, maybe bio or cyber or events like pandemic and epidemics, which ultimately paves the way for apocalypse and extreme species on Earth for no fault of others. Rest in peace and harmony. Today, made it in 22 minutes.